The following reaction has an activation energy of 262 kilojoules per mole. At 600 Kelvin, the rate constant is 6.1 times 10 to the minus 8 per seconds. What is the value of the rate constant at 730 Kelvin? So this is an application of Arrhenius' equation, which states that our rate is some factor times e to the minus activation energy over RT. And just for completeness, although R is fine to use here, this sometimes is written as KT. But K and R, K being Boltzmann's constant, they're the same constant, just different units. Okay, so we're going to write out some of the values here. So we have K1 is equal to 6.1 times 10 to the minus 8 per seconds. T1 is 600 Kelvin. K2 is our unknown, and T2 is 730 Kelvin. So if we write this out, we have K1 is equal to A e to the minus EA over RT1, and K2 is equal to A e to the minus EA over RT2. Now if we divide these two, K1 over, I better make sure I follow my solution a little bit, K1 over K2, okay, so then these A's will cancel. And dividing exponentials means you can subtract their factors. So you end up with an exponential minus EA over R, 1 over T1 minus 1 over T2. So we subtract them, which would turn this positive, but if I'm taking a negative EA over R out, that will turn it back to negative. So there's our expression there for dividing the rates. And then now we want to solve for our K2, or I guess what I did was just solve for this. So K1 over K2, so inserting our values. I'm going to use, so the EA given is this 262 kilojoules per mole. R is 8.314 joules per mole Kelvin. So we're going to need to multiply by 1,000 joules per kilojoule here, just to get rid of the kilojoules, and the joule will cancel there, the per mole will cancel. Giving a Kelvin up top, and then this is 1 over 600 Kelvin minus 1 over 730 Kelvin, meaning everything's just going to, all the units are going to cancel, which is good. When we take an exponential, we want it to be unitless. Running this all through our calculator, we get e to the minus 9.3532, which is 8.6687 times 10 to the minus, no, times 10 to the minus 5. Okay, so then rearranging for K2, K2 is K1 over 8.6687 times 10 to the minus 5, which equals this 6.1 times 10 to the minus 8 per seconds over this factor, which comes out to be, and rounding to two significant figures, because that's all we were given in the K1, 7.0 times 10 to the minus 4 per seconds. Okay, so there's our K2 through from the Arrhenius equation. So that's our rate constant at 730 Kelvin. So going to the solution here, so you could solve for the prefactor, but you don't need to. And then you can, so that's what they did here, was solve for the prefactor and then use that in Arrhenius' equation to solve for the K. But it comes out to be 7.0 times 7 minus 4, so that looks good.